Okie dokie. Welcome everybody to the in the room and at home. I'll wave. And on our stream. So today it's my pleasure to introduce Professor Sugata Kaviraj, who did his PhD in Oxford. Boo, no, sorry, just kidding. And then he did some fellows in Oxford, and fellowships in Oxford and UCL and Imperial before settling down in Hertfordshire, where he has been since 2013 and is now a professor. He's an expert in galaxy formation and approaches from both the observational as well as the theoretical side. And he's going to tell us all about dark matter-deficient dwarf galaxies today. So if you have questions at home, please put them in the chat. I should be able to see them.
Thank you. Is it okay if I take my mask off?
Yes, it is.
Okay, great. All right, okay, thank you, Annalise, for the introduction. It's great to see people in 3D rather than 2D, which we've all been doing for, God knows how long. And it was really good to interact with some of the students today, so thank you all for coming. Okay, so today I'd like to talk about these dark matter-deficient dwarf galaxies, okay? And so I was going to say, if you please interrupt during the talk. So I don't have that many slides, so I'm happy to take questions as we go along as well. Okay, so I'd like to talk about these dark matter-deficient dwarf galaxies. So this is a new phenomenon, a fairly new phenomenon, and some people have postulated that the existence of these dark matter-deficient dwarf galaxies may pose a challenge to lambda CDM. Okay, so what I'll do in this talk is I'll kind of lay out why the existence of these galaxies may be problematic, and then I'll show you using a cosmological simulation that actually the presence of these dark matter-deficient dwarf galaxies is not likely to be a challenge to lambda CDM. Okay, so this work has been done by my student Ryan Jackson, so I should say ex-student. He's just finished and started his fellowship last week. So this is Ryan Jackson's work, and it's been done in collaboration with the New Horizon project, which is the cosmological simulation that I'm going to use. Okay. All right. So before we start talking about these dark matter-deficient dwarf galaxies, let's just talk about dwarf galaxies in general, right? So why do we care about dwarf galaxies? Why are they important? So if you think about the galaxy mass function, right? This is the stellar mass function. At all epochs and in all environments, dwarf galaxies dominate, right? So lambda CDM is hierarchical. Small things form first. Large things form later, and so dwarf galaxies dominate the number density, right? At all epochs and all environments, when you look at, let's say, the mass function, the stellar mass function, there are many, many more dwarfs than there are massive galaxies, right? So what that means is that if you want to understand, galaxy evolution, if you want to understand the physics of galaxy evolution, you need to understand how the dwarf end of the mass function is actually forming, right? Because they are the most numerous type of object in the universe, and so we do need to understand how these objects form. And so what that also means is that discrepancies in what you observe in dwarf galaxies and what you predict can constrain theory as well, right? So they become good theoretical probes of how structure forms in the universe. All right. So as an aside, well, actually, this is not an aside, this is potentially an important point. So even though dwarf galaxies dominate the number density, if you think about surveys, right, our statistical understanding of galaxy evolution is predicated on surveys, right, large surveys, wide area surveys. It turns out that past wide area surveys, for example, let's say the Sloan Digital Sky Survey, which some of you might have used, like the SDSS, these past wide surveys are actually too shallow to reveal dwarfs at cosmological distances, right? So i.e. things which are outside the local group, right? So let me explain this using this plot. So I'm plotting stellar mass, log of stellar mass on the x-axis, okay, and the effective surface brightness of the galaxy, right? So that's the surface brightness within one effective radius, right? And one effective radius is the radius that roughly contains half the light of the galaxy, okay, or half the mass, if you want, right? So this is a measure of the effective this is the effective surface brightness, and this is the stellar mass, right? And if you think about dwarfs, what we're talking about are galaxies which are essentially lower than about 10 to the 9 solar masses, right? So that's roughly what I'm calling the dwarf regime, right? So the dwarf regime roughly starts here, right? To the left of 9 is dwarfs, to the right of 9 is what I would call massive galaxies. So these red lines here show you what the detection limits are, roughly, of different surveys, right? So for the SDSS, the detection limit is roughly here, right? So then now the surface brightness limit of SDSS is about 26.5, but galaxies start becoming highly incomplete in SDSS around 24.5, right? So after an effective surface brightness of, so galaxies which have fainter surface brightnesses, or surface brightnesses fainter than 24.5, are essentially not in the SDSS at all, right? Now, if you look at this line, right, and you look at where, so what this means is that your object will have to be above the line to be detectable, right? So anything which is below the line, in principle, is not going to be detectable. So if you have to be above the line, then at 10 to the 9 solar masses and above, most of the galaxies in the universe are detectable by SDSS, right? So SDSS is good for massive galaxies. But when you go to the left of 10 to the 9, most of these galaxies are actually below the SDSS line, right? So some are, of course, not, right? There are some dwarfs which do climb above this line, but these dwarfs tend to have anomalously high levels of star formation. And if you look at the simulation, what causes these anomalously high levels of star formation are interactions and mergers, right? But the point is, you can't use these guys to draw any conclusions about the generic properties of dwarfs in general, right? Because these dwarfs, which are visible in SDSS, are highly anomalous, right? So you shouldn't be doing dwarf galaxy studies just using SDSS, in other words, okay? Okay, so we have a situation where we know that dwarfs dominate the number density of the universe, but you can't see most of the dwarfs in a universe using past-wide surveys, right? Now that's a problem, because what that means is that you're not going to be able to test properly your theoretical models, right? Because you need the data to test it, but you don't really have the data if you consider these past-wide surveys. So perhaps it's not surprising that many of the tensions in LCDM that you might have heard about, things like the missing dwarfs, the missing dwarfs problem, right? So this is a mismatch between the number of dwarfs that are predicted in the simulations compared to what you see. There's a problem called the core cusp, right? So you predict something, you predict a more peaked distribution in the matter in these objects. The lack of AGN in dwarfs, and also dark matter deficient dwarfs, which I'll talk about. So perhaps it's not surprising that many of the tensions in LCDM appear in this regime, right? Because this regime is not really testable using the surveys that have gone in the past, like SDSS. Now, just as an aside, this is actually about to change, right? So if I showed you the same line for the legacy survey of space and time, LSST, that line is going to be here, right? At around 29.5, let's say, okay? So what this tells you is that in LSST data, in principle, anything which has a stellar mass of 10 to the 7 at low redshift, lowish redshift, right? And we're considering redshifts of, let's say, about 0.2, will be visible in this survey, right? So for the first time, you're going to have the capability to see most of the dwarfs in our universe in these wide area surveys, right? So in this decade, we're going to have the possibility of comparing our models properly to, in a statistical fashion, essentially, to survey data, okay? So in some ways, these dwarfs, the dwarf regime is, in some ways, a new frontier in our study of galaxy evolution, right? So in this era of deep wide surveys like the SDSS and high resolution simulations that we can now run, we're going to, in principle, learn a huge amount about how galaxy evolution takes place by looking at how dwarfs evolve in the low and intermediate redshift universe. Okay, so let's talk about these dark matter deficient dwarfs, right? So why might these objects pose a problem? So because these dwarfs have shallow potential wells, it's much easier to perturb or expel gas in these galaxies, right? So what happens when you perturb the gas, let's say you increase the turbulence of the gas, or you perhaps expel the gas altogether, what you will do is you will affect the star formation rate, right? So no gas equals no star formation, okay? So in lambda CDM, dwarf galaxies are expected to be dark matter rich. Maybe that's not the right way to say it. Actually, they're expected to be star poor, right? So they're supposed to have, their star formation is supposed to be quenched earlier, because it's easier for baryonic feedback to either perturb the gas or expel it. And so so the expectation is that these dwarf galaxies, generally speaking, should have fewer stars per, let's say, unit dark matter, okay, than, let's say, massive galaxies. So if you think about the mass function, there's a sweet spot where the feedback is least effective, right, around about the knee of the mass function. And then as you go further away from the knee, as you go to the massive end, AGN feedback becomes more important. And as you go to the left of the knee, we think that stellar feedback is what causes produces the feedback that regulates the star formation. But anyway, so these dwarf galaxies are expected to be dark matter rich, right? So if you find a substantial population of dwarf galaxies which are not dark matter rich, then in principle it could pose a problem for this standard paradigm. Okay? And indeed, recently, people have claimed to have found, or people have found, dwarfs which have dark matter to stellar mass ratios of around unity. Right? So the ratio of the dark matter mass to the stellar mass is about 1. Right? So in principle, these galaxies have dark matter fractions which are 400 times lower than what you would expect. Okay? So the question then is this an issue? Right? So you expect in this paradigm that you're going to have, that your dwarfs are going to be dark matter rich, because you're going to be able to essentially quench star formation more easily, but you find things which are not only are they not dark matter rich, they are extremely dark matter poor, right, compared to the stellar mass. Okay? So that's the fundamental question. Is this an issue? Okay. So as we said, it's difficult for galaxies which are essentially rich in baryons to form in halos which are deficient in dark matter, right? That's the fundamental problem here, okay? And so this is a potential challenge to the standard model. So before we discuss, the way to work out whether this is an issue or not is to, of course, look for channels which may form galaxies, dwarf galaxies, which may be dark matter poor, right? So it's not the case that channels, these types of formation channels are not known. There are some formation channels that we know about which will form dark matter poor objects. But the question is, do they form, do they produce the dark matter poor population that you see in the observations, right? Are the numbers correct, et cetera, et cetera? Okay. All right, so let's look at some of these channels, okay? So one channel, which has been known for a while, are called tidal dwarfs. Right? So what are these tidal dwarfs? So when you have a merger between two massive galaxies, so typically these have to be sort of massive gas-rich galaxies. These gas-rich galaxies come together, and material is ejected in these tidal tails, right? And what happens is that you get gene instabilities in the gas in these tails, right? Essentially what's happening is the gas is flowing out in these tidal tails. So the gas which is at the base of the tail is moving faster than the gas which is further away in the tail, okay? And you get compression, right? And when you get compression, you're gonna you might trigger star formation, and you may form something which has the mass of a dwarf galaxy, right? You're going to form a small, a low mass object. And if this low mass object has escape velocity, eventually it will start self-gravitating and it will become a bona fide dwarf galaxy, right? And hopefully you can see why this dwarf, this tidal dwarf, is not going to be dark matter rich. And the reason is that it isn't forming by baryons accumulating in a dark matter halo, right? It's forming essentially in the tidal tail, where these regions are not necessarily, they don't contain dark matter halo, right? So these tidal dwarfs are not going to have much dark matter. So that's one way of forming a dwarf galaxy, which is not going to be dark matter rich, right? So by construction, these galaxies are going to be fairly dark matter poor, right? They're going to be rich in stars, but not in dark matter. Okay, so great. So this is a potential formation channel. But of course, the question is, do you form the right numbers, right? So you have a channel of forming these, let's say, dark matter deficient dwarfs via these, via this tidal channel, but how many do you actually form? So theory predicts this, and observations actually show this, right? So these are SDSS images of merging galaxies, right? Very, very local merging galaxies. So of course you might ask the question, well, do you actually see this in the observations? And the answer is yes, you do. So these are all either merging or systems in the process of merging, or they are kind of like post mergers, right? Like this guy here. But in each of them, you can't really see this very well probably on the screen, but the red circles indicate separate photometric objects that the SDSS pipeline has picked out. Okay, so these are like tidal dwarf candidates. You don't know whether they're going to turn into tidal dwarfs or not, but it's clear that you form pockets of stuff, right? And these are all stars essentially, right? They're not going to have much dark matter. Okay, so these tidal dwarfs are forming clearly in these observed gas-rich mergers. Now the problem is, if you actually look at the frequency of the tidal dwarfs, it's extremely low, right? So you can't really create the population of dark matter deficient dwarfs that you're looking for using this tidal channel, right? So the tidal channel clearly does produce some dwarfs, but it has lots of other problems. And of course, the other big problem, which you can probably see, is that most of these guys may not end up existing as separate objects, right? Why? Because they're just going to be reaccreted by the massive object, and they will essentially disappear, right? So it's very hard, in other words, to form enough tidal dwarfs, which then self-gravitate to satisfy the dark matter deficient dwarf population that you expect to see. Okay, so this channel is plausible, but it doesn't really work. Okay, so there are other channels which have been proposed. So another channel which has been proposed is essentially a high-velocity collision between gas-rich dwarfs, right? So you have two dwarf galaxies, they collide with each other. So these the relative velocities are probably 300 kilometers per second or higher. So what happens is something like what's shown here. Okay, so you have this collision, and the dark matter essentially separates from the disk gas, right? So think of the bullet cluster, right? Some of you might have heard of the bullet cluster. You have these two clusters. So the dark matter and the stars essentially just fly through each other, right? Now the gas, because it's not interacting just by gravity, it's also interacting by the EM force. So that makes the gas sort of stickier. So the gas kind of collects in the middle, right? And then the gas can then form stars. Okay, so think of this as like a miniature version of the bullet cluster. Okay, so the dark matter will separate from the disk gas. Okay, so the dark matter is in blue, so it separates from the disk gas, and the disk gas accumulates in the center, and then is shock compressed to form stars. Okay, so the end result potentially is that you have a clutch of stars forming, right? So that's your new dark matter deficient dwarf, but the dark matter that you had in the original dwarfs has essentially flown past, and it's separated from the gas and the stars. Okay, so it's like a miniature bullet cluster. Okay, so maybe this is another formation channel. The problem with this channel is that these simulations are idealized, right? So what they've done is they've essentially they're looking at something which is not taken from a cosmological simulation, right? So they're just looking at a specific configuration, which they have essentially imposed on the system, and they're asking the question, can this collision form a dark matter deficient dwarf? So clearly it can, but the question you have to ask is, what is the collision cross-section of this kind of process? And it's extremely unlikely, right? So if you look at the cosmological simulation, you cannot really have, you don't really have these kinds of collisions very frequently. Okay, so again, a plausible channel, but it doesn't really work. Okay. Now, so basically what this tells you is that in principle, it's easier to form these dwarfs if they were normal to start with, right? So if you had dwarfs which are normal to start with, in terms of, let's say, the dark matter content, but there was some process which was fairly common, right, and operates on these dwarfs for essentially a sustained period of time, then you might be able to remove the dark matter, and you were able to remove the dark matter over time while not affecting the stars too much, then that would be a plausible channel. That's the only way, really, of producing this population of dark matter deficient dwarfs, okay? So one obvious option is tidal stripping, right? And so we know that many of these dwarfs are in orbit around massive galaxies, right? Because massive objects capture low mass objects, so they end up in orbit around these massive galaxies. And these dark matter halos are much more extended, right? So when you look at the stellar content of any object, the halo is much, much more extended than that, right? So if the dark matter halo of this dwarf is much more extended than the stars, then in principle it will be more susceptible to stripping, right? So you'll be able to access the dark matter halo. So the massive companion will be able to access the dark matter halo much more easily than it can access the stars, right? So maybe you will strip the tidal, you will tidally strip the dark matter, but you will not touch the stars, right? So the stellar mass may be roughly the same, or may escape unscathed from this collision, but the dark matter will not, right? So the dark matter will get stripped, but the stars will not get stripped, okay? So this is a plausible channel, right? But the question then is, can it form dwarfs which are severely deficient in dark matter, right? When you compare to the observations, how many are expected to form? How long do they survive, right? Because again, think of this as a, it's possible that this process is transient, right? Because if these dwarfs are in orbit around these massive companions, maybe these massive companions will essentially accrete the dwarfs, right? So they will disappear from the universe at some point, right? So the question then, so you have to answer all of these questions to work out whether this mechanism is viable within lambda CDM. So what do you need for this, to answer this question? What you need is you need a cosmological simulation, right? You need a simulation that has a cosmological volume because you want to study this process in a statistical way, right? And you need something which is a hydrodynamical simulation, right? Which has high mass and spatial resolution. So you need a cosmological volume for your statistical study. You need a high mass and spatial resolution to resolve your dwarfs, right? Because what we want to do is not just look at dwarfs at the present day, but we want to trace their progenitors back through time, okay? So if your simulation doesn't have good enough mass and spatial resolution, you're not going to be able to do that, right? So as an aside, if you, lots of you have probably heard of simulations like illustrious Eagle, Horizon AGN. So these simulations, for example, had, let's say, spatial resolutions of about 1 kiloparsec, right? Now, if you think about the Milky Way scale height, it's about 300 parsec, right? So, so these large box simulations don't really give you the kind of spatial resolution you need to study dwarf galaxies, right? Either in the space, either the resolution in spatial coordinates or the resolution in mass. And of course, you need the hydrodynamics to have spatially resolved predictions for the baryons, okay? So what we're going to do is we're going to use a simulation called New Horizon, which is it's a high resolution sphere of about 10 megaparsec radius, taken from an average density environment within a larger box simulation. Okay, so the larger box simulation is Horizon AGN. The box size is about 100 megaparsec on a side, and we are essentially resimulating an average density environment from Horizon AGN at higher resolution, right? So what kind of resolutions are we talking about? So the dark matter resolution is 10 to the 6. The stellar mass resolution is 10 to the 4. So if you think about, I don't know, a dwarf galaxy which has a mass of 10 to the 8, you're going to have enough particles to resolve that dwarf galaxy, okay? And you're going to also have enough particles to resolve the progenitor of that dwarf galaxy, because of course the progenitor is going to be smaller, right? So you need to have enough resolution to start with to actually resolve these things back through time, okay? And then the spatial resolution is about 34 parsec, roughly 40 parsec, right? So if you compare the 40 parsec to 1 kiloparsec, you can see why you need this kind of sort of resimulated volume for this kind of exercise. Okay? So one thing to bear in mind is that because the volume is small, what you tend not to have are the rarer objects, right? So the rarer environments like clusters just don't exist in this simulation. Okay? So there are no clusters in this volume. So if you think about a 100 megaparsec volume, you're going to have essentially one cluster in this large box simulation, right? But there are no dense environments or highly dense environments in this resimulated volume. So the maximum halo mass, if you want to think about it in terms of halo masses, is about 10 to the 13, right? So you're looking at groups in the field, right? So the question we're trying to ask is, can you produce dark matter deficient dwarf galaxies in groups in the field using this simulation? Right? That's the question we can answer using this simulation. So you might think, well, I want to look at clusters, right? Because you just told me that tidal stripping is likely to be more efficient in higher density environments, right? But that is not a question you can answer using this simulation. What you can do, though, is if you can show that dark matter deficient dwarfs form in a lower density environment, then you can kind of assume that they will form in higher density environments as well. So maybe it's not a question that you need to answer separately. Okay, so the rest of what I'm going to show you is going to be based on this New Horizons simulation. All right, so yeah, so okay, I guess I can show you some pretty pictures. So if you look at simulations like New Horizon, so here's the cosmic web, and you can produce galaxies which look fairly realistic, right? They're much more realistic than the, let's say, previous generation of simulations like Horizon AGN, Eagle, and Illustrious. All right. Okay, so we have the simulation, and so remember that the question we're trying to answer is, can we form dark matter deficient dwarfs in lambda CDM within this simulation, right? So the first question to ask is, well, do dark matter deficient dwarfs exist in simulation? If the answer is yes, then we can then look at these objects and work out what the differences are between the formation of these objects and the stuff which is not dark matter deficient. So this is a plot of the halo mass, right, the dark matter halo mass on the x-axis, and the stellar mass on the y-axis. Okay, so the dark matter deficient territory is about here, right, where the dark matter to stellar mass ratio is about 10 or lower, right? So remember that you expect much higher values than 10 normally when these things sort of start their lives at in the early universe. So you can clearly see that there are things which you would call dark matter deficient, right? And because we're looking at the entire halo, if you then measure the dark matter within a smaller aperture, of course, it'll, these ratios will be even smaller. So there are clearly some dark matter deficient galaxies in this simulation. Okay, so what we do is we split the population into essentially three groups. So so what you see here is that the open circles are what we call central galaxies, and everything else are what we call satellites, right? And that's a theoretical definition in the sense that something becomes a satellite when its dark matter halo is accreted by the halo of something else, right? A bigger galaxy, essentially, right? So if that's not the case, right, if your dark matter halo is not part of something else's dark matter halo, then you are a central. Otherwise, you are a satellite. Okay. So what you find, not surprisingly, is that all these dark matter deficient dwarfs are actually satellites, right? So the stellar stuff of the galaxy hasn't been accreted, but the dark matter halo is actually already part of the dark matter halo of a massive companion. And as you'll see, as I'll show you as I go through the plots, this is essentially what's doing the tidal stripping and forming this dark matter deficient population. Okay, so just to set up those definitions, so I'm going to call dark matter deficient galaxies. So these are the blue ones here. And these are defined as anything where the dark matter to stellar mass ratio is less than 10. Okay? And you can see that there are some galaxies which have extremely low values, right, of order unity, as observations have found. Then we're going to define a control sample. Right? Now this control sample is going to be composed of satellites which are consistent with the relation which is defined by the centrals, right? So if you just look at the centrals, you see that there's a fairly tight relationship between the dark matter to stellar mass ratio and the stellar mass, right? So if you just look at the open circles, you see that the relationship is fairly tight, right? And there are some satellites, the ones in orange, which are also on that relation, right? And actually, the reason things scatter off that relation, as I'll just show you in the next slide, is because of dark matter stripping, right? Dark matter is removed, and so as dark matter is removed, things will move to the left. Okay, so this is the dark matter deficient population. This is the control population, right? The satellites which are like the controls, like the centrals in their dark matter content. And everything in between is what I'm going to call, dark matter poor, okay? So the satellites essentially, the controls essentially don't have much dark matter stripping. The dark matter poor galaxies have a bit more dark matter stripping, and the dark matter deficient galaxies have more dark matter stripping than that, okay? So what we're going to do is we're going to compare the formation history of these dark matter deficient dwarfs to the control sample, essentially. And you'll see that the dark matter poor population essentially falls somewhere in between, as you would expect it to. Okay. Okay, so let's start with, so the first question that's worth asking is, are there differences in the stellar evolution, right? So we're talking about dark matter a lot, but maybe the stellar evolution of these galaxies is slightly different, right? So you're talking about a ratio, dark matter in the numerator, stars in the denominator. So it's worth checking whether the stellar evolution shows any differences as well, okay? So if you plot the median stellar mass evolution of all these populations, you find that they are very similar, okay? So if you look at these, this is the median, so the cumulative evolution, if you like, of all these different classes, right? The control sample in orange, the dark matter poor in green, and the dark matter deficient population in blue, right? They all kind of correspond to each other. So what this tells you is that the dark matter deficiency is not due to differences in star formation, right? The star formation properties of these galaxies is basically similar throughout time, okay? Now, when you look at the dark matter halo, the halo mass of these galaxies, you start seeing differences, right? So if you look at the the control sample, which is in orange, right? So remember that the control sample is composed of satellites which show the same kind of dark matter properties as the centrals, right? So these are things which haven't really had much dark matter stripping. So the control sample is in orange. And if you compare the control sample to the dark matter poor in green and the dark matter deficient in blue, what you clearly see is that in the dark matter deficient and dark matter poor populations, there is a decrease in the halo mass, right? So the dark matter is being removed, right? So gradually these things lose their dark matter mass. After about a redshift of 1, it starts accelerating, right? So at late epochs, the halo mass of these dark matter poor and dark matter deficient galaxies start to decline fairly sharply, okay? And that drop in the dark matter halo mass drives the change in the ratio between dark matter and stars, okay? So this plot is basically a consequence of that one, okay? And as you would expect, the controls and centrals do not show a decrease in halo mass, and so their dark matter to stellar mass ratios remain fairly flat. Okay. All right, so it's clear that the dark matter, it's clear that the evolution of the dark matter properties is what's driving this dark matter deficiency, right? So the question is then why, right? What are the details of the process which is driving this dark matter, this decrease in the dark matter halo mass? So if you look at the locations of these dark matter deficient dwarfs, right, what you find is that they exist everywhere in the simulation, right? So that they don't exist just at the edges of the simulation where you would expect some edge effects, right? So we should do some sanity checks to check whether these things could be artifacts, okay? So they exist everywhere in the simulation, so they're not driven by edge effects. And the reason it's worth pointing this out is because in some other simulations, people have tried to look for dark matter deficient dwarfs. They've found them, but they tend to be just on the edges, right? And at these edges, weird things happen. Okay, and the reason weird things happen is because at the boundary, you have an intersection of a higher resolution volume with a low resolution volume. So you can have low resolution dark matter particles traveling through your galaxy, and that can do weird things to your galaxy. Okay, so it's worth checking whether these dark matter deficient dwarfs are artifacts or not. Okay, so they exist everywhere in the simulation, and the other thing that's worth mentioning is that they have what we call 100% purity in dark matter. So this is a technical thing, but essentially what that means is that they are not contaminated by these low resolution dark matter particles, right? So if you think about the setup, you have this high resolution region surrounded by a low resolution box, okay? And so in the low resolution box, you have dark matter particles which are, each particle is much larger, right? So when one of these particles flies through your high resolution dwarf near the edge of the of your sphere, then it can do weird things to your galaxy. For example, it can mess your galaxy up, if you like, right? Simply due to the gravitational effect of this low resolution particle flying through. Okay, so it's necessary to check that all the dark matter particles in these dark matter deficient dwarfs are actually high resolution dark matter particles, right? So you don't have contamination from the low resolution box which surrounds your high resolution region. Okay, and the third sanity check is that the dark matter mass decrease is gradual. It's not abrupt, because if it was abrupt, then the suspicion would be that it's some sort of misallocation of dark matter by the structure finder, right? So you have two objects which are where we already know that this smaller object is a satellite, right? So it's been absorbed. So the dark matter halo has been absorbed by the dark matter halo of the bigger galaxy. So it's important to check whether the structure finder is misallocating dark matter particles from one object to the other. Okay? Because if you did that, then of course you can abruptly change the dark matter mass of the smaller object. But what we find throughout, and I'll show you the typical evolution in the next slide, is that the dark matter the dark matter mass change is gradual, right? So that tells you that it's not some sort of artifact driven by misallocation of dark matter. Okay, so we've done some checks to ensure that these things are not artifacts, and they clearly are not artifacts. Okay, so they are a bona fide population that seems to form naturally in the simulation. Okay, so let's look at the density. Right? So if you look at the local dark matter density around both the dark matter deficient and dark matter poor populations, what you find, not unexpectedly again, is that the dark matter densities are higher, right? Okay, so if you compare that to, let's say, the centrals or the control sample, what you find is that the local dark matter density around these two populations, the dark matter deficient and dark matter poor dwarfs, is elevated. Okay, so that tells you that density is playing a role. And going back to the last image, what you find also is that these populations tend to favor the nodes of the cosmic web, right? So the nodes of the cosmic web are obviously where the densities tend to be higher. So so this is x versus y, y versus z, and x versus z from the simulation volume. What you find is that they tend to congregate in these node regions. Okay. So the differences in dark matter that you find between these populations are somehow connected to local density. So it's all pointing in the same direction, essentially. Okay. Fine. So we think that there is a connection to the density. So the next obvious thing to do is to try and parameterize this process, right? So you need to find a way of measuring the tidal field, right? Because maybe it's just not one companion, maybe the tidal stripping is being done by multiple companions, right? So what we want to do now is, since we think that the dark matter deficiency is driven by density, what we want to do is look at the specifics, the details of that density, right? The details of the tidal field around these galaxies, which may be creating this dark matter deficiency over time. So what we do is we set up something called a perturbation index, which is a measure of the strength of the tidal field, right? So essentially this PI, this perturbation index, measures the tidal field, and of course it's a function of both the mass of the perturber, right? So this is the ith perturber, and the distance that perturber is away from you. Okay? So this is the galaxy in question, right? This is the mass of the dark matter halo of the galaxy in question. This is the virial radius of the galaxy in question. And mi and di are the mass and distance of the perturbing galaxy. Okay? So what we're going to do is we're going to look at the pi created by the massive companion, right? The companion of which the dwarf is actually a satellite, and also the pi generated by the ambient tidal field. So the question we're trying to ask is the pi evolution different for dark matter deficient dwarfs compared to, let's say, the control sample? Right? Okay, so here are examples of how the different properties change for a dark matter deficient dwarf compared to a control. Right? So on the first, on the top row, row 1 is stellar mass. Right? So you can see that dark matter deficient dwarf carries on forming stars in roughly the same way as the control. The halo mass drops, which we've seen before, right, from the median curves that I showed you. The dip in the halo mass happens when the halo level in the simulation changes from 1 to 2. Now that happens when you go from being a central to a satellite, right? So what this is telling you is that up to this point, this dwarf was a central, right? So it hadn't been absorbed by, so its dark matter halo wasn't absorbed by the dark matter halo of a massive galaxy. At this point, it becomes a satellite, right? So the halo level becomes 2. That's this terminology, right? There's no physical meaning to these numbers. So halo level equals 1 means you're a central. Halo level equals 2 means you're a satellite. So at the point where it becomes a satellite, it starts shedding dark matter, right? Dark matter starts to be removed from this galaxy. Okay? Now, if you look at the pi, what you see is that when this happens, the pi from larger galaxies, and this is usually just the massive companion of that dwarf, rises, right? And not only does it rise, it shows a consistent rise. Okay? So the stripping of dark matter, or rather the loss of dark matter, coincides with this dwarf becoming a satellite, and the pi, the perturbation, the tidal field, the strength of the tidal field from the nearby massive galaxies showing a spike, right? And that pi remains high throughout the rest of the lifetime of this galaxy. Okay? And then what you find, as you would expect, is that the dark matter to stellar mass shows a corresponding decrease, right? Because the stellar mass hasn't been affected. It's still forming stars, right? The stellar mass is still going up. But it's losing dark matter, right? And this discrepancy is then driving this ratio downward. Right? What you might notice as well is that not only is the stellar mass not being affected, it's accelerating, right? So the star formation rate is the gradient of this plot, essentially, right? So actually, what the tidal perturbation is doing is it's removing dark matter, but it's also creating stars. It's giving the star formation a kick. Okay? So I'll come back to this in one of my last slides, because this could also be important when we compare to observations. Because we see in the observations that actually the number of star clusters that you see in these dark matter deficient dwarfs is slightly elevated. And it may be due to the fact that these tidal perturbations are elevating the star formation at the same time as stripping the dark matter. Now, if you look at the control galaxy, the behavior is very different, right? So you don't see any dark matter stripping, and the pi is basically flat, right? The pi from massive galaxies, this orange line here, doesn't really show any change. And of course, as a result, the dark matter to stellar mass ratio of this dwarf galaxy remains within the typical sort of median bounds of the dwarfs. Okay, how am I doing for time? Okay, all right. Okay, so if you summarize this in terms of the total pi and the pi from the massive companion, what you find is that the dark matter differences between these populations are connected to the tidal perturbations from these nearby massive companions. Okay, so it's the tidal perturbation from the nearby massive companion which is essentially driving this dark matter deficiency. Okay, so I think I probably need to speed up a little bit. So the next question is, what does that actually mean, right? So is it the properties of the massive companion? Are the massive companions, for some reason, larger in these dark matter deficient dwarfs? And is that why the PI is actually larger? So when you look at the properties of the massive companion, you don't really see any difference between the stellar mass or the halo mass of the massive companions of these dark matter deficient dwarfs compared to the halo and stellar mass of the control galaxies, right? Of the nearest massive companion of the control galaxy. So what that tells you is that the dark matter deficiency is not due to differences in the properties of the massive companion. Right? So the only thing that's left then is the orbit, right? So what this means is that when you look at the orbits of the dark matter deficient and the dark matter poor dwarfs compared to the control sample, which remember are the satellites which are not stripped, what you find is that these dark matter deficient dwarfs come much, much closer to their massive companions than the control sample. Okay? So the massive companions themselves are no different between the different populations, but the orbits are very different. Right? So in the dark matter deficient dwarfs, the orbits are much, much closer, so the orbits are different in the sense that they come much closer to the massive companions than in the other populations. Right? So if you looked at the minimum distance divided by, let's say, the virial radius of the massive companion, they are much smaller in the dark matter deficient galaxies than in the control galaxies. Okay, and then finally, if you want to look at where the dark matter is being stripped, as you would expect, it takes place largely, mainly at large radii, right? As you would expect, because remember that the dark matter halos are extended, and so the halo is much more susceptible to the tidal stripping than the rest of so the outskirts of the halo, rather, are more susceptible to the stripping than other parts of the galaxy. So the dark matter stripping takes place in these outskirt regions preferentially, where the dark matter particles are essentially more loosely bound, right? This is where you would expect the stripping to take place. Okay, so given that these dark matter deficient galaxies are in tight orbits, it's worth considering how long they will survive, right? Because these guys eventually could be accreted by the massive companions. So actually, when you look at the simulation, let's say you look at a snapshot at redshift of 0.7, what you find that only 30% of dark matter deficient galaxies which exist at a redshift of 0.7 are still there at a redshift of 0.25, right? So over a period of, let's say, 3.5 gigayears, you have lost 70% of your dark matter deficient dwarfs, right? So these guys, they have essentially disappeared into the massive companions. They've been accreted, right? So this process of creating dark matter deficient dwarfs is actually a constant process, right? So these guys are created, most of them are accreted by the massive companions, but then new ones are formed, right? And then these new dark matter deficient dwarfs replenish the supply, if you like, of dark matter deficient dwarfs in the universe. So this is a constant process within lambda CDM, right? So you shouldn't think of these dark matter deficient dwarfs as a static population, right? Some sort of static special population. It's just a natural byproduct of galaxy evolution. Okay, so let's have a look at some images. So these are two dark matter deficient dwarfs. Just to show you what these interactions look like. So these are just stars. So the reason we haven't shown dark matter particles is because the frame will be filled with dark matter particles because there's so many more. So this is the kind of interaction you're talking about, right? Here's your dwarf. Here's your massive galaxy. The dwarf is essentially flying through the massive galaxy here, or it actually is behind the massive galaxy. Here's the virial radius of the dwarf, okay? And so you can see that as the interaction progresses, the virial radius of the dwarf is smaller than it started with. Okay, so in this case, it's reaccreted some dark matter particles, but you can see the change from the first snapshot to the second one. And in this one, the process is more gradual. So this is actually a group of galaxies, and the dwarf is basically flying through this group. And as it exits on the other side, it has clearly lost a fair fraction of its dark matter halo. Right? So the virial radius was here, whereas now it's here. Right, so finally, let's talk about observational work. So the problem here is that, as I said at the beginning, you're looking for features which are very faint, right? You're looking for these tidal features, as I showed you in the previous slide, which are extremely faint. Okay, so these types of tidal features are very, very hard to see in, let's say, SDSS. Okay, so the SDSS really doesn't have the depth to show you this kind of tidal feature. So the question is, how do you test this, right? I mean, what you really need to test this is something like LSST, right? Something which has a lot of depth and a lot of area, so you can collect a lot of these dark matter deficient dwarfs, right? So maybe you can identify dark matter deficient dwarfs and then go away and look at deep imaging to check whether they have these tidal features or not. Okay. So one group has done this on a much smaller scale. So they've looked at one dark matter deficient dwarf galaxy. So Montes et al. 2020. So they've looked at very deep optical imaging of one of these dark matter deficient galaxies, DF4, and they found that there is clear evidence for tidal stripping. So when you measure the shape of this dark matter deficient dwarf, you find that it's elongated along this axis, and it seems consistent with the orbit of the dwarf around this massive galaxy. But this is only essentially one example. Okay. So it seems to support what we're saying theoretically, but more work is obviously needed. Going back to this star formation rate issue that I mentioned, so the other thing that people have found is that there's an excess number of star clusters around these dark matter deficient dwarf galaxies. Okay, so it could be that this tidally induced star formation that I talked about, right? If you think about the evolution that we were talking about, where the stellar mass, the star formation rate was seen to be elevated after the tidal interaction started. So this could be why you have these excess number of star clusters in these dark matter deficient dwarfs, right? So essentially what's happening is that the tidal perturbation not only is it stripping dark matter from the outskirts of the halo of the dwarf, it's also inducing star formation within the dwarf. And that extra star formation, if you like, is giving you these excess number of star clusters. Okay, good. So I think I'm at the end. So here's the summary. So as I said at the beginning, in lambda CDM, dwarf galaxies are expected to be dark matter rich, right, or rather star poor, because feedback, it's easier for feedback to perturb the gas or expel the gas. So you expect these things to be relatively dark matter rich compared to their stellar populations. But you have these recent observations of dark matter deficient dwarf galaxies that that appear to challenge this paradigm. But if you look at a high resolution simulation like New Horizon, what you find is that gradual tidal stripping of dark matter by massive companions in dwarf galaxies basically produces what you see in the observations, right? It produces naturally produces a population of dark matter deficient dwarfs. Right? But the thing to remember is that this is a continuous process, right? So these things are not some sort of special, tail end of the distribution kind of thing. They are just natural byproducts of galaxy evolution in the hierarchical paradigm. Now, of course, this is what I've shown you guys is a theoretical study, right? It needs to be tested further with deep surveys, and the data doesn't exist to do that yet. But as far as the existence of these dark matter dwarf galaxies is concerned, contrary to what some people have said, the existence of these types of galaxies is not really in tension with lambda CDM. In fact, they form naturally in lambda CDM in fairly appreciable numbers. Thank you. I'll stop there.
Thank you. Your timing is impeccable. So we'll go over to questions now. If you have questions here, yeah, no problem.
I was going to ask, how do you solve the boundary conditions if you've got a sphere and then you've got low resolution particles flying in from the low resolution region? How is that usually solved?
Yeah, so I mean, so what we...
Could you repeat the question for the people?
Yes, so the question was, yes, I guess the solution, yeah, okay. So let me paraphrase what you said. So is it a problem that you have a high resolution sphere embedded in a low resolution box, right? It could be. What we do is we essentially ignore galaxies which have any dark matter impurity. So I don't think you can solve it necessarily. But it just so happens that none of the dark matter deficient dwarfs that we have in our sample have any contamination at any point in their lives. I think that's just lucky, probably. That's just luck. But yeah, I mean, you have to live with that problem, because you are going to have, at the edges of the high resolution region, there will be some galaxies which are contaminated by low resolution dark matter.
Is there any reason why the sphere is better than the box?
No, it was just picked as a sphere.
So something you showed quite nicely is that the efficiency of tidal stripping is basically just the gradient of the potential. So the more massive the galaxy or the closer in you get, the more efficient it is. But presumably that means that your best stripped galaxies are the most bound things, kind of all the satellites. So how do you square that with the fact that some of these very dark matter poor things are seen in the field?
Yeah, so I think, yeah, that's a good question. So,
Can you repeat that?
yeah, sorry. I think, so the question was, why do you find some of these dark matter deficient dwarfs in the field, right, where you would not expect that kind of tidal stripping? Okay, so I think the answer is, if you think about the differences between, let's say, a cluster and a field, in a cluster, the relative velocities are higher, right? So the amount of tidal perturbation that you experience, it's not just dependent on the distance, it's also dependent on your relative speed with your companion, right? So what we actually find, so I don't have a plot, so I can't show you the plot, but I can send it to you offline if you're interested. What we find is that the total amount of tidal perturbation that a typical dwarf experiences in the field and in a cluster is actually not that different. Because in the field, the relative velocities are slower, and so it's spending more time close to these companions, right? Whether they're massive companions or equal mass companions, it doesn't really matter. So it is possible to have a fair amount, to experience a fair amount of tidal perturbation even in low density environments. And the reason, part of the reason, is that the relative velocities are lower, and so you kind of linger around companions longer, and that can cause, you know, things like tidal stripping of dark matter, if that makes sense.
But you would still expect there to be a massive companion there.
Say again, sorry?
Even if it's in the field, you would still expect a massive companion.
Yeah. I mean, nothing is completely empty, right? I mean, if you think back to the, let me take you back to the, yeah, so I mean, in this volume, you know, it's not selected to be a void, put it that way. I mean, there are probably voids in there. And perhaps you're right that in a void-like region, maybe dwarfs they're not going to have any tidal stripping. But usually, whatever, regardless of environment, and it is slightly counterintuitive, but what we found is that if you look at dwarf galaxies in general in the simulation, regardless of where they are, what their local environment is, the amount of tidal perturbation that they experience over a fairly long period of time is not that different. It's not a strong function of environment. So yes, you could have, you could create these galaxies even in sparse environments.
Last question. Putting the simulations to one side, do we have observations of lots of dwarf galaxies that are dark matter rich?
I think so the question is, do we have observational evidence of lots of dwarf galaxies which are dark matter rich? I think the answer is indirectly yes, because people are assuming that they're all dark matter rich.
Well, that's my concern. Is the assumption, because we do know that, for example, a lot of the clusters are essentially dark matter free.
Yes.
There's increasing evidence that a lot of other smaller elliptical galaxies are
Dark matter free, yeah.
Because I mean, that indeed would be the most useful way
Yes,
of
indeed.
demonstrating that conclusion.
Right.
By finding that the ratios of dark matter rich and
Yeah.
dwarfs make sense.
Yeah. So ideally what you actually want to do is you want to look at the distribution, the predicted distribution of dark matter to stellar mass ratios, and then compare that with an observational sample where you had enough to do statistics with. I don't know the answer to that question, I'm sorry, but because I don't work on observations of dwarf galaxies.
I don't work in the field, that's why
Yeah. That's an excellent question. But yes, I completely agree. I think, yeah, you need to look at the full spectrum of properties and compare theory to observation. Yeah.
Yeah, I know there's a couple more questions, but there's no questions online. But we reached the hour, so I suggest we just try to ask your question politely after the talk.
Yeah, we can go offline, yeah, sure.
Let's thank Sugata again. Yeah, the Zoom is